Hello everyone, I am Mr. P. Mabuhussain, Assistant Professor of EEE from Institute of Aeronautical Engineering, Hyderabad. Today in this video, we are going to discuss about the numerical problems of on capacitance of a transmission line system. So the learning outcome of this lecture is that by the end of this lecture, the students will be able to solve the problems for calculating the capacitance of any type of transmission line. So any type of transmission line here in the sense, the transmission line may be a single phase transmission line or it may be a three-phase transmission line. So in three-phase, you have a symmetrical three-phase transmission line and asymmetrical three-phase transmission line and a double circuit three-phase transmission line. For all these type of lines, we are going to calculate the capacitance. So first see the numerical problem 1. So the problem here is that a single phase transmission line has two parallel conductors 3 meters apart. So radius of each conductor being 1 centimeter. Calculate the capacitance of the line per kilometer. So given that epsilon naught is 8.854 into 10 to the power of minus 12 farads per meter. Okay, so here the transmission line is a single phase transmission line in which you have the two parallel conductors. Now these two parallel conductors are at a distance 3 meters apart. So the capital D here is, or you can get a small d. So d is equal to 3 meters. So this small d represents the distance between the two conductors. And radius of each conductor is given as 1 centimeter, which is r is equal to 1 centimeter. Now you have to calculate the capacitance of the line per kilometer. Okay, and the value of epsilon naught is also given here. In some problems, the value of epsilon naught is not given. So you have to remember this value. The value of epsilon naught, it is always a constant. The value will be equal to 8.854 into 10 to the power of minus 12 farad per meter. Okay, so this is the epsilon naught value which you have to remember, right? Sometimes in the problem this value is not given, though here in this problem it is given. So in some other problems the value is not given. Okay, so if you see the solution, the radius or the conductor radius is given as 1 centimeter and the spacing between the conductors or distance between the conductor is given as 3 meters, right? So now this meters is converted into centimeters by multiplying this value with 100. So you will get 300 centimeters. Now the capacitance of the line formula is pi epsilon naught by ln d by r in farads per meter. Okay, so this is the capacitance of the line, which you can also call it as line capacitance. So this is the line capacitance. So if you want the per phase capacitance, then the value is CAN will be equal to 2 pi epsilon naught by ln d by r farad per meter. Right? So if they were asked to find out the per phase capacitance, you have to use this formula. So here in the problem, they asked to find out the calculation of capacitance of the line. So here is line capacitance. That line capacitance equation is C is equal to pi epsilon naught into ln d by r in farads per meter length. This value is only for 1 meter length. Okay, now you know the value of epsilon naught, which is 8.854 into 10 to the power of minus 12. Ln d here is 300 meters and r is 1 centimeter. So 300 centimeters and 1 centimeter. So if you substitute the values and calculate, so then you will get the value in farads per meter. So the value here we are getting is 0.4875 into 10 to the power of minus 11 farads per meter. Okay, so now here in the problem they asked to find out the capacitance value for 1 kilometer. So you have to multiply this total value with 1000 so that value will be the capacitance for 1 kilometer. So the capacitance per kilometer will be 0.4875 into 10 to the power of minus 8. So farads for 1 kilometer. Okay. So if you convert this into microfarads, so then you will get this value, so which is 4875 into 10 to the power of minus 2 microfarads per kilometer. Okay, this is how you can determine the capacitance of a single phase transmission line. So remember that if they ask you to find out the line capacitance, so the line capacitance of the line, so this value will be always equal to pi epsilon naught by ln d by r. Okay, so capital D here is the distance between the two conductors and r is the radius of the conductor. So if they ask to find out the per phase capacitance C phase, then this equation is 2 pi epsilon naught into ln d by r. Okay, this is the equation. So both values are farads per meter. Okay, so you have to remember these equations. Right. Now let us calculate the capacitance for a three-phase transmission line. And here in this numerical problem, a three-phase overhead transmission line has its conductors arranged at the corners of an equilateral triangle of 2 meters side. Okay, here you have a three-phase transmission line, which is a overhead transmission line, and the conductors are arranged at the corners of an equilateral triangle like this. Okay, and the triangle is having a side of 2 meters. So this side is 2 meters, this side is also 2 meters, this side also 2 meters. That means if the conductors are represented with A, B, C here, so then the distance between A, B, B, C and C all will be the same. So this type of configuration is called the symmetrical spacing of conductors. Now for this configuration, you have to calculate the capacitance of the each line conductor per phase. Each line conductor here is nothing but the value is per phase capacitance. Okay, calculate the capacitance of each line conductor per kilometer they asked. So here each line they are asking, so you have to find out the per phase capacitance C phase, or you can that may be represented with CAN or CBN, CCN like that. Okay, so which is nothing but capacitance between phase A and neutral, capacitance between phase B and neutral, capacitance between phase C and neutral. These are all called the per phase capacitances. Okay, so now given that the diameter of each conductor is 1.25 centimeter. Okay, so here the diameter is given, then you will get the radius of the each conductor. So right, the radius of each conductor is r is equal to diameter by 2. So which you will get 0.625 centimeters. And spacing between the two conductors, it is given as 2 meters. So once if you convert the meters into centimeters, then you will get the distance between the two conductors will be 200 centimeter. So the capacitance of the each line, which is nothing but per phase capacitance, the value is 2 pi epsilon naught by ln d by r. So here if you observe the problem, the value of epsilon naught is not given. So in the previous problem, the value of epsilon naught is given in the problem itself. So but you have to remember that the value of epsilon naught is always constant, and the value will be equal to 8.854 into 10 to the power of minus 12 farads per meter. So this value always may not be represented in the problem. So you have to remember this value. Okay. So now the value of D is given, the value of R is also given. So you can substitute all the values in this formula. You will get the value of capacitance per phase or value of capacitance for each line. Okay. So that value here we are getting it to be 0.0096 into 10 to the power of minus 9. The value is in farads per meter length. So but here they asked to find out the capacitance for 1 kilometer. So for getting the capacitance value for 1 kilometer, you have to multiply this total value with 1000. Once you multiply this value with 1000, then this value will become 0.0096 into 10 to the power of minus 6 farads per kilometer. Okay, so this is the farads per kilometer. Okay, on 10 to the power of minus 6 in place you can write micro. So the value of capacitance per phase will be 0.0096 microfarads per kilometer. Okay, so this is how you can determine the capacitance of a three-phase overhead transmission line if the spacing between the conductors is same. So that means the symmetrical spacing of conductors is given. So then you have to proceed like this. Let us see another problem. So here the problem is in a three-phase 50 Hz 66 kV overhead line conductors. Overhead line conductors are placed in a horizontal plane, which is as shown in the figure here. Okay, so the conductor diameter is given as 1.25 centimeters, and if the length of the line is 100 kilometers, calculate the capacitance per phase, charging current per phase, assuming that complete transposition of the line. Here they are giving that the conductors of a overhead transmission line are arranged on a horizontal plane. So like this is one conductor, this is another conductor, this is one more conductor. All the three conductors are arranged on a horizontal plane, and the distance between the conductors is also given here. Suppose if it is A, B and C, three conductors are there. So then the distance between AB is given as 2 meters, and B into BC is given as 2.5 meters, and A to C is given as 4.5 meters. Okay, and the diameter of the conductor is given, which is 1.25 centimeter. So once you know the diameter, you can calculate the radius. So the radius of each conductor R will be equal to 1.25 by 2. So the value you are getting here is 0.625 centimeters. Okay, so the conductor spacing is different for different conductors. Suppose if you take conductor A and B, the distance is 2 meters. B and C is 2.5 meters, and A to C is 4.5 meters. So here in such a case, how you can calculate the capacitance. So the capacitance for phase for this type of configuration is you can also call it as asymmetrical configuration. Why? Because if you observe the distance between any two conductors, that value is not same here. Okay, so in such a case, for a asymmetrical three-phase transmission line, the value of per phase capacitance you can determine by using the formula CAN is equal to 2 pi epsilon naught by ln D equivalent by R. Okay, and here the value of D equivalent is nothing but, so this value is D12, D23, D31 whole to the power of 1 by 2. Suppose if the conductors are represented as 1, 2 and 3, so then D equivalent will be equal to D12, D23, D31 whole to the power of 1 by 2. Okay, so D12 here is nothing but distance between 1 and 2 conductor. D23 is distance between 2 and 3 conductors. D31 is distance between 3 and 1 conductors. Right, from the diagram here, you will know all these three values, D12, D23 and D31. Right, you simply have to substitute the values so that you will get the value of D equivalent. Okay, so the value of D equivalent are simply they are calling here as a D. Okay, so that value is cube root of D1, D2, D3, and D1 is distance between 1 and 2 conductors, which is 2 meters. D2 is distance between 2 and 3 conductors, which is 2.5. D3 is distance between 3 and 1 conductor, which is 4.5. Okay, if you calculate this value, you are getting the value to be equal to 2.82 meters. Right. So now this is in meters. So if you want to convert this into centimeter, this value will be 282 centimeters. So that is only represented here. Okay. So once you know the D equivalent, so this is nothing but they represented D equivalent as D, which is equal to D1, D2, D3 whole to the power of 1 by 3, and this D1 is nothing but this distance, D2 is this distance, D3 is this distance. Okay. So then the capacitance equation, line to neutral capacitance or per phase capacitance. So that value will be equal to 2 into pi epsilon naught by ln D by R in farads per meter. So here 2 pi, the epsilon naught value is always 8.854 into 10 to the power of minus 12 by ln, and the value of D here is nothing but D equivalent, which is 282 centimeter, and the value of R here is 0.625 centimeters. Okay, now if you calculate this total value with the calculator, so then you are getting the value of per phase capacitance in farads per meter. So the value of per phase capacitance here we are getting is 0.0091 into 10 to the power of minus 9 farads per meter. So now if you want the value for entire transmission line, right? If you observe the entire transmission line, the length of the transmission line is given as 100 kilometers. Okay, so 100 kilometers in the sense, so in terms of meter, 100 into 10 cubed meters you will get. Okay, so now you got the capacitance value for 1 meter. Okay, so this value is for 1 meter. Okay, if you want for 1 kilometer, you have to multiply this value with 1000, so that you will get this value 0.0091 into 10 to the power of minus 6 farad per kilometer, right? This is the value of capacitance per phase per kilometer. Okay, so 10 power minus 6, you can even write it as micro, so that you are getting this value 0.0091 microfarads. On this value is for 1 kilometer only, but our length of the transmission line is 100 kilometers. So for 100 kilometers transmission line, the value will be this 0.0091 microfarads multiplied by 100. So the value will get 0.91 microfarads. So this is the per phase capacitance of a total length of the transmission line. Okay, so in the problem they also asked to find out the charging current per phase. So now the charging current per phase IC, it will be equal to V phase by XC here. Okay, so V phase by XC is the charging current, right? So now this V phase by, so XC here is nothing but 1 by J omega C, or you can even simply call it as, you can omit this J so that you will get the magnitude of IC. So 1 by omega C. So this can be written as omega C V phase. So C here is nothing but per phase capacitance, which is the CAN. Okay, so M omega is nothing but 2 pi f. So 2 pi f into CAN into V phase, right? So but here, if you observe, the transmission line is a 3-phase transmission line, and the line to line voltage is given, which is 66 kV. So 66 kV is the line voltage. So phase voltage will be equal to 66 by root 3. Okay, 66 by root 3 kV here. So or you can even write it as 66,000 by root 3 volts. Okay, so this is the V phase value. Now this XC can be written as 1 by omega C. When it comes to the denominator, this will become omega into CAN. So this omega you can write it as 2 pi f. So the 2 pi f into CAN you will get 2 pi f C you will get here. And frequency is given in the problem itself, which is 50 Hz. Right. So then the value of C is 0.91 microfarad. So if you substitute all the values here, the frequency and capacitance values, so then the value of charging current you will get. So that value will be equal to 10.9 amperes. Okay. So this is how you can determine the per phase capacitance of a 3-phase transmission line when the spacing is asymmetrical. Okay. So for a asymmetrical 3-phase transmission line, you can calculate the per phase capacitance like this, and you can even calculate the charging current per phase also. For calculating the charging current per phase, the formula is always same. IC is equal to V phase by XC for any type of transmission line. Now let us see the another problem. So this problem is related to the bundled conductors. Okay. So here once read the problem. Figure shows a completely transposed 50 Hz 250 kilometers long 3-phase line having flat horizontal phase spacing with 10 meters between adjacent conductors. If the outside radius is 1.2 centimeters and the line voltage is 220 kilovolts, determine the charging current per phase of the line. Okay, they asked to find out the charging current here. So the charging current is equal to V phase by XC, which is equal to V phase by 1 by omega C, which is equal to omega C into V phase. Right? If you want to know the value of charging current IC, you must know the omega. Omega here nothing but 2 pi f C into V phase. Okay. So for calculating the IC, you need to know the frequency, and the frequency is given in the problem, which is 50 Hz, and you should know the V phase. So V phase value you can determine from the line voltage. Okay, line voltage is given as 220 kilovolts. So V phase is equal to 220 into 10 cube by root 3 volts. Okay, you will get the V phase, and you need to calculate the capacitance. Per phase capacitance you have to determine. Right? So you need to determine per phase capacitance initially for calculating the charging current. How do you can determine the per phase capacitance for this type of transmission? Okay. So now if you observe the transmission line configuration here, so each phase, so this is one phase, this is one phase, this is another phase. This is a 3-phase transmission line. Okay. So 3-phase transmission line. In each phase, you are having 2 subconductors. So this type of configuration is called the bundled conductor configuration. Okay. So so this transmission line is a 2-conductor bundled configuration, and each conductor is a stranded conductor. Okay. So this is a stranded conductors, and this is all the conductors. If you see, all the conductors are stranded conductors. Okay. So whether they are given as a solid conductors or standard conductor, it is not a matter for us. So you have to consider that this standard conductor is one subconductor, this is another subconductor. 2 subconductors are there in each phase. Okay. So which is called the 2-conductor bundle configuration transmission line. Okay. For such type of lines, how you can determine the capacitance? Okay. So for determining the per phase capacitance, the equation is same. So CAN is equal to 2 pi epsilon naught by ln D equivalent by R. So D equivalent by DS here, right? So if your transmission line is having only one conductor for each phase, so then this denominator you have the value R. Okay. So if you are having more than 2 conductors, in such a case you always use the self GMD or the mutual GMD method. So in self GMD, mutual GMD method, if you use, then the value of capacitance will be 2 pi epsilon naught by ln dm by ds you have to write. And dm is the mutual GMD and ds is the self GMD. And this dm value you can also call it as D equivalent. So which is nothing but equivalent equilateral spacing, and that value will be equal to D12, D123, D31 whole to the power of 1 by 3. Okay. And ds you have to calculate for a 2-conductor configuration bundle. Okay. So let us see how we can determine the capacitance of this type of transmission line. So now the capacitance, if you observe, you need to find out the dm and ds here. How you can determine ddm, how you can determine ds. Okay. As I said before here, so dm value is equal to D equivalent, which is equal to D12, D23, D31 whole to the power of 1 by 3. Right. So now this D12, so D12 is nothing but center to center distance between 2 conductors A and B. Okay. So here the conductors are represented with A, B, C. Right. So here this equation even can be written as DAB, DBC, DCA whole to the power of 1 by 3. So if the conductors are represented with the numbers, then you can use this equation. If they are represented with the ABC, then you can reach this equation. Now DAB is the center to center distance between phase A and phase B. Right? Phase A center is this one, phase B center is this one. So this 10 meters is the DAB value you can consider. And from B to C, the center to center distance is again 10 meters. The value will be DBC. So similarly, from center to center distance from C to A will be DCA. So which will be equal to, so this 10 plus this 10, which is total 20 meters. Okay. So the value of DM is equal to 10 into 20 whole to the power of 1 by 3. Okay. So 10 into 20 whole to the power of 1 by 3. So if you calculate this value, what you will get? So you will get around 12.6 meters. Okay, 12.6 meters is the DM value. Okay, so this is the one method for finding the DM value. You also have the another method also. So another method also I will explain. So in the another method, what you have to consider? You have to consider DAB, DBC, DCA. So DAB is nothing but this is the mutual distance by considering the conductors A and B. So in such a case, A is having AA dash, B is having BB dash. So all mutual distance you have to take product of all mutual distances DAB, DAB dash, DA dash B, DA dash B dash whole to the power of 1 by this 2 into 2, 1 by 4 you will get. Okay, so all the distances if you observe, so then you will get these values, and you are getting DAB is equal to 9.995 meters, and this DAB and DBC if you observe, those two values will be the same, and DCA if you calculate, then you are getting about 19.997 meters, right? This 9.995 is nothing but approximately equal to 10 meters, and this value is approximately equal to, so this value approximately equal to 20 meters, right? So this value also approximately equal to 10 meters. So you will get the same again. Okay. So D equivalent. So if you use this method, the value you are getting it to be 12.594 meters. Suppose if you are doing in the previous method, what is the value you are getting? So this value you are getting 12.6 meters. Okay. So this method is the approximate method actually, and this method is the exact method. So but if you observe the two values, you will get almost the same value. Okay, so I always prefer to use this method so that the problem will be solved very easily. Okay, so now from this dm is equal to d equivalent is equal to 12.6 meters. Okay, so then after calculating this, you have to calculate the ds. So ds is nothing but self GMD. Self GMD you can calculate by considering the each phase. Okay, so if you consider the first phase, you are having two conductors A and A dash. So the value of self distance ds is equal to, you have to consider all the distances, all the distances product you have to consider daa distance, dab, d b, sorry. So here A and A dash conductors are there. So the value of ds is equal to daa, d a dash, d a dash a dash, d a dash a whole to the power of 1 by 2 square, as there are two conductors. Okay, and daa and d a dash is will be equal to r into, then what is the a to a dash distance? So if you see the figure here, a to a dash distance, center to center distance will be 0.4 meters it is given. So that 0.4 meters you can substitute here. So this is 0.4 meters. So now a dash will be r again, a to a dash is 0.4 again, whole to the power of 1 by 4. So this value is equal to r into 0.4 whole square whole to the power of 1 by 4 you will get. So this value again will be equal to 0.4 into r whole to the power of 1 by 2. Okay, so r into 0. So what is the r here? So here in the problem, if you see, outside radius is given here. Outside radius is 1.2 centimeters. Okay, so 1.2 centimeters you can substitute here. Okay, then the value of ds is equal to 0.4 into 1. So see here, so this 0.4 is in meters and the value r is in centimeter, but you have to use only one terminology only, whether it is meters or centimeters. As 0.4 is in meters, you also convert the value of r into meters only. Okay, so r value is given as 1.2 centimeters. If you convert that value into meters, then you have to multiply with 10 power minus 2 or divide with 1.2 by 100 you will get. So that value is 0.012 meters. Okay, 0.012 meters. So here 0.012 you have to write. Okay, so whole to the power of 1 by 2. So this is the value. So underscore it 0.012 into 0.4. So the value, if you calculate, you are getting the value of dsc will be equal to 0.0693 meters. Okay, the value of ds in meters and the value of d equivalent or dm will be also in meters. Okay, so then the per phase capacitance you can calculate by using this expression. Can is equal to 0.0242 by log d equivalent by ds, and this value is in microfarads per kilometer. So directly in terms of microfarads per kilometer you will get. Suppose if you use another equation, Can is equal to 2 pi epsilon naught by ln dm by ds. So this value will be in farads per meter. You can use any equation. You can use this equation and you can convert that again into kilometers and microfarads. Okay, or you can directly use this equation also. CAN is equal to 0.0242 by log D equivalent by DS in terms of microfarads per kilometer. Okay, so I'm using this equation right now. So now here D equivalent is nothing but 12.6 meters and DS is nothing but 0.0693. You substitute the values and you calculate this total value. So then you will get the CAN in terms of microfarads per kilometer will be 0.0107096 you are getting. Okay, so this is the value for 1 kilometer. Okay, so capacitance value in microfarads per 1 kilometer. So but the transmission line here, if you observe in the problem, the transmission line length is a 250 kilometers length transmission line. Okay, so now you got the capacitance for 1 kilometer. Now if you multiply with the 250, you will get the capacitance for 250 kilometer length transmission line. Okay, so here you have to multiply this total value with 250 so that you will get the capacitance per phase for entire transmission line in terms of farads. The value you are getting here is 2.677 into 10 to the power of minus 6 farads. So this can even be written as 2.677 microfarads. Okay, and they also asked to find out the charging current. And the charging current expression is omega into CAN into VLN. So VLN is nothing but V phase. Okay, and this is equal to 2 pi F into CAN into V phase. And the value of V phase, how you can determine? This V phase is equal to VL by root 3. So in the problem itself, they given the 220 kilovolts, which is the line voltage. So V phase will be equal to 220 by root 3 in kilovolts you will get. And CAN value we are calculated here. And if you substitute all the values, and frequency also 50 Hz it is given in the problem. If you substitute all the values here in this equation, you will get the charging current. And the charging current you are getting here is 0.1068 kilo amperes. And this charging current is for one phase. Okay. So this is how you can determine the capacitance of a transmission line if the conductors are bundled conductors. Okay, if each phase is having bundled conductor configuration, so then this is the procedure to calculate the capacitance. So finally, let us determine the capacitance for a double circuit transmission line. Okay, so here in this problem, you need to determine the capacitance and charging current of a 200 kilometers long transposed double circuit 3-phase line, which is as shown in the figure here. Okay, so the line operated at a 220 kilovolts and the radius is 2 centimeters it was given. Okay, and the distance, so this type of that transmission line, double circuit transmission line derivation we already discussed in the previous video. So I am using the direct formulas here. Okay, so here it is the 3-phase double circuit transmission line. When it is transposed, one section, so one section 1 is given here, section 2 and section 3 is not given. So section 1, section 2 and section 3, out of all the 3 sections, only one section is given here, and one section data is enough for the calculation of capacitance. Okay, so now the formula for calculating the capacitance of a double circuit transmission line is also the same. So CAN is equal to 0.0242 by log D equivalent by DS in terms of microfarads per kilometer. Okay, and here the value of D equivalent is nothing but DAB, DBC, DCA whole to the power of 1 by 3, and the value of DAB here is the mutual GMD again. So this DAB is the mutual GMD by considering the phases A and B. So DBC is the mutual GMD by considering B and C. DCA is the mutual GMD by considering C and A. Okay, so how we can calculate the mutual GMD here? So in a double circuit transmission line, A will be having A dash, B is also having B dash subconductors. So then mutual distances will be DAB, DAB dash, DA dash B, DA dash B dash. All these products whole to the power of 1 by, so here 2, here 2, 2 into 2, 4. So 1 by 4 you will get. Okay. So like this, you can calculate the value of DAB. Similarly, the value of DBC by considering the phases B and C, and DCA by considering the phases C and A. So these are the equation for calculating the DAB, DBC and DCA. So now here DAB, DB, these are the distances. Okay. So now here if you see, so the value of DAB, so for calculating DAB, so what is the distance? So distance from A to B. If you observe, so this is the phase A, this is the phase B, this is the phase C. In the reverse direction, A dash, B dash, C dash. These will be there. Okay. So DAB distance. So DAB distance is D here. Okay. So this value is D. Okay. So you substitute all the values. Okay. So that D here, it is represented with this is the 4 meters, that distance. So this distance is 4 meters. And this total distance is 9 meters. Okay. So this total distance is 9 meters here. So then what is this distance? You have to calculate. So this distance you have to calculate. Okay. So by considering this rectangle, triangle. Okay. So what is this value? This value is 4. And here if you see, half of the value is 4.9, 4.5. So this is also 4.5 here. And this distance is 7.5. So see here, the configuration is given like this one. Okay. So this is A, B, C, A dash, B dash, C dash. So this distance is given as 7.5. And this distance is given as 9 meters. Okay. So then so this distance from here to here, it is 7.5. Right. So 9 minus 7.5, if you see, what you will get, this value will be 2. So 1.5 will get. So 1.5. Okay. So now this 1.5 will be this value plus this value. So half of this value will be this value. So which is 0.75. So this value is 0.75 and this value is also 0.75. Now this distance. So here this distance is given 4 meters. This distance is given 4 meters. So this is capital D. So the capital D value will be equal to 4 square plus 0.75 whole square. So right. So by using this equation, you can calculate the value of D. So the value of D, what you will get once if you calculate this value, it is 4.0697 meters you will get. Okay. So here the value of DAB. So this distance is nothing but capital D, and D A to B dash. So A to B dash here is A is it here it is, and B dash is here it is. So what the value of D2 you have to find out. Okay. So you have to take any rectangle and then you have to calculate the D2 value. So like that you have to determine all the distances. Okay. After determine all the distance, you have to simply substitute here. Okay. So that you will get DAB, DBC and DCA values. Okay. Once you are getting DAB, DBC, DCA values, and if you substitute all of them in this equation, then the value of D equivalent you will get. So the value of D equivalent, finally you are getting it to be equal to 6.61 meters. Right. So I'm requesting you to calculate all the distances, these distances, and find out these values. Okay. So then only you will get the D equivalent finally. So the final value I'm giving here, which is D equivalent is equal to 6.61 meters. So then self GMD, for calculating the self GMD, ds is equal to dSA, dSB, dSC whole to the power of 1 by 3. So here also, so dSA is the self GMD, dSB is the self GMD, dSC is the self GMD by considering phase A, phase B, phase C. Okay. So phase A is having A to A dash. So dSA will be equal to all the distances you have to consider: DAA, D, A dash, D, A dash, A dash, D, A dash, A whole to the power of 1 by 4. 1 by 2 square you will get, 1 by 4 you will get. So DAA, D, A dash, A dash, this value will be R. Right, R. And what is the distance? D, A to A dash is D3. Okay, so this is also R into D3 you will get whole to the power of 1 by 4. What is this D3? So D3 from this diagram. Okay, A to A dash is this D3. Okay, so DSA finally will get R D3 whole to the power of 1 by 2. Okay, similarly for DSB R into D4 whole to the power of 1 by 2 you will get. For DSC you will get R into D3 whole to the power of 1 by 2. Okay, so now you have to find out what is the value of D3, D4 and D3. So these values from this diagram here. So from this diagram you have to find out the values of this D3, D2, D4 and D5. Okay, so by taking any one rectangle triangle, so that you will get the value of DSA, DSB and DSC. Okay, once you get the value of DSA, DSB, DSC here, then the value of DS will be equal to DSA into DSB into DSC whole to the power of 1 by 3. You substitute all the values here, and so that you will get the value of DS, and finally I am given here the value DS is equal to 0.453 meters. Okay, so D equivalent is 6.61 meters, DS is 0.453 meters. Okay, right, then the value of per phase capacitance CAN is equal to 0.0242 by log dm by ds, and the dm value is 6.61, ds is 0.453, so which is in microfarads per kilometer. Okay, so once you calculate this total value, you are getting 0.02078 microfarads per kilometer. Okay, so this is the per phase capacitance, and charging current you can determine using this formula, which is equal to, so this is the magnitude of charging current, omega into CAN into V phase. Okay, 2 pi f CAN into V phase. Okay, as you already know, the value of line voltage is 220 kilovolts. So V phase is 220 by root 3 kilovolts you will get. Okay, and frequency is given. Frequency here it is not given in the problem. So you assume that the frequency will be equal to 50 Hz if it is not given. Okay, so then you simply substitute the all values here in this equation. You will get the value of charging current. So magnitude of charging current, you are getting the value to be 0.1658 kiloamperes per phase. Okay, so this current is for one phase. So this is how you can determine the capacitance of a different transmission line system, right? So we have seen the capacitance for a single phase transmission line, three phase transmission line if the conductors are placed symmetrically, and three phase transmission line when the conductors are placed on a horizontal configuration, which is nothing but asymmetrical configuration. And also we have seen that a single phase we also seen that capacitance of a three phase transmission line having the conductors as a bundled conductors, and then we have seen the capacitance of a double circuit transmission line. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.